This is part 2 of the lecture on selection of independent variables for investigating causal relationships. In this section, we discuss typical steps of statistical investigation of hypothesis on causal relationship between two variables, with focus on selection of other variables for multivariate analysis. Let's start with the classical issue of causation versus association. It is widely agreed that a statistical association between variables does not necessarily mean there is a causal relationship between them. So, should we not use statistics when we are investigating causal mechanisms of empirical phenomena? In reality, we use statistics a lot. Why? Suppose we have a hypothesis on causal mechanisms of some empirical phenomena. Then we look at data on the empirical phenomena, and the data may show a statistical association that is consistent with the hypothesis. If so, the statistical association lends support to the hypothesis. Of course, a statistical association, expected on the basis of a hypothesis, never proves that hypothesis to be true, but it makes the hypothesis more plausible. A lack of the expected statistical association usually makes the hypothesis questionable. For example, suppose we hypothesize that cigarette smoking raises the risk of lung cancer. Well, this has been so firmly established that it should not be called a hypothesis anymore, but let's call it a hypothesis for now. The hypothesis may make us expect a higher incidence rate of lung cancer among smokers than non-smokers. But if we don't find a higher rate among smokers, the hypothesis is not considered as plausible as expected. In general, this is an issue in the philosophy of science. Empirical evidence never proves that the hypothesis is true, but it raises the plausibility of the hypothesis. Support from a greater amount of data increases the plausibility of the hypothesis. If the support comes from diverse types of data, in different populations during different periods, the plausibility of the hypothesis is raised even more. Some types of data give stronger support than others. Usually, experimental data lend stronger support than observational data, and longitudinal observational data lend stronger support than cross-sectional observational data. Now, let's go through typical analytic steps when we investigate a hypothesis on a bivariate causal relationship. Suppose there are two variables, x and y, and we hypothesize that x causes y, or that x affects y. We may sometimes investigate a more complicated hypothesis, but in this session, let's focus on hypotheses in simple forms. Suppose also that y is a numerical variable, and linear regression is considered a major tool of our multivariate statistical analysis. Usually, our first step is to examine statistical association between x and y, without involving any other variables. If we find a substantively and statistically significant association between x and y in the expected direction, that will support the hypothesis. Usually the direction is important. We expect a higher incidence rate, not a lower incidence rate, of lung cancer, for smokers than non-smokers. In an introductory statistics course, we study major methods of examining bivariate associations, such as t-test for difference between two means, one-way analysis of variance, two-way contingency table, and simple linear regression. But the statistical association between two variables may be affected by other variables. For example, the smoker population and the non-smoker population may have different statistical profiles with respect to some characteristics, which may directly or indirectly affect the risk of lung cancer. So, as for step 2, we may examine the association between x and y, controlling for the plausible confounders. Multiple linear regression is a widely used statistical tool for this purpose. If we find a substantively and statistically significant association between x and y, in the expected direction, controlling for some plausible confounders, we have further support of the hypothesis. Then, in step 3, plausible mediators are included, in addition to the plausible confounders in step 2. Comparison of regression analysis results at step 2 and step 3 gives us an estimate of the extent to which effects of x on y work through those mediators. So, results of step 3 help us to understand mechanisms through which x affects y. This is called mediation analysis, which is discussed in more details in epidemiological method courses. If we have multiple mediators, we may include them together at the same time, add them to the model one by one, or do separate regression for different mediators, depending on the purpose and hypothesis. By the way, research note assignments for this course require knowledge up to step 2. Step 3 covers mediation analysis and it is beyond the scope of this course. There are some important lessons and cautionary notes related to these steps. First, it is important to select plausible confounders for step 2. Generally, a strong bivariate association between x1 and y lends support to the hypothesis that x1 affects y. But the strong association may be due to some confounders. Thus, if we find a strong association between x1 and y, controlling for some plausible confounders, it will lend stronger support to the hypothesis than a simple bivariate association does. Second, we should strictly distinguish plausible confounders and plausible mediators, and we should be careful not to include plausible mediators in step 2. What we want to get in step 2 is the best estimate of total effects of x1 on y. But if some mediators are included in the regression model, the regression coefficient of x1 reflects effects of x1 on y, excluding those that work through the mediators. Inclusion of mediators in step 2 is likely to lead to underestimation of overall effects of x1 on y. Third, an outcome of y, denoted here as x4, should not be included in the regression model at any step of the investigation. For example, if the dependent variable is blood glucose, then diabetes status should not be included in the regression model. If x4 is included, the regression coefficient of x1 does not reflect effects of x1 on y that lead to x4, but reflects only the effects of x1 on y that do not lead to x4, which may possibly be a small fraction of total effects of x1 on y. This slide shows results of a simulation conducted in order to understand problems with inclusion of an outcome of y in the regression model. In this simulation, artificial data were produced using the two regression equations, y equals 10 plus 2 times x1 plus residual, and x4 equals 5 plus 0.5 times y plus residual. So, these are the true underlying mechanisms. x4 is an outcome of y, so it should not be included in regression of y, but suppose we mistakenly included x4 as an independent variable. The true value of the coefficient of x1 is 2. So estimated values of the coefficient from regression analyses using the simulated data should be around 2. But we got 1.01, 0.87, 0.90, 0.99, 0.94, 1.26, 0.88, and so on. The estimated values were around 1, notably underestimating the effect of x1 on y. This problem occurred because x4, an outcome of y, was included in the regression equation predicting why this lesson may seem to be clearly understandable. But it is not unusual to see this kind of error in works by beginners of data analysis, such as inclusion of diabetes status in a regression model of blood glucose. Some cautionary notes need to be added to the lessons just described. First, it is important to be aware that issues discussed in this section are relevant only if regression analyses are used for investigating causal relationships among variables. In an earlier session, we studied that there are two major objectives of regression analysis: prediction and investigation of relationships among variables. They are not relevant if regression analyses are used for prediction only. For example, the level of prostate-specific antigen, PSA, in blood should be included in an equation predicting prostate cancer status from data from blood and urine tests. A raised PSA level may be an outcome of prostate cancer, but it does not matter in this case, because the purpose of the regression equation is prediction. By the way, this prostate cancer example does not really fit linear regression, and actually fits logistic regression better, but the principle is the same. Second, it should be kept in mind that partial regression coefficients are estimated, controlling for variations with respect to the particular forms of the confounder included in the regression model. For example, suppose we are interested in causal relationships between x and y, and included education as a plausible confounder. Suppose that the variable, education, is a categorical variable with 3 categories: not having graduated from high school but not from college, and graduated from college. Inclusion of this variable in regression of y adjusts the coefficient of x for differences among these 3 groups, but not for other aspects of education. Some students may drop out of high school when they are 9th graders, and some may do so when they are 12th graders. High schools are very different in many aspects. Some colleges are more competitive than others. Even among students at the same college, those with different majors may have quite different educational experiences. All these are educational differences and may be exerting confounding effects on the relationship between x and y. Inclusion of the education variable may remove confounding effects of differences among the 3 groups, but the regression coefficient of x may still be confounded by many other aspects of education, even though tables of the published paper are accompanied with a note that the results were adjusted for education. Thirdly, Lesson 2 does not include a mediator in Step 2, but actually a mediator could be included in Step 2, if the study focuses on a particular pathway of X, and if the mediator is not considered to be on the pathway. Suppose we hypothesize that education reduces the risk of obesity, because education helps to raise the level of concern about weight control and the level of knowledge on health problems of obesity. Suppose the data include income as a variable. Should income be included in the regression analysis of BMI for investigating the hypotheses? Income should not be included in the regression model if our focus is on overall effects of education on BMI. If it were included, the partial regression coefficients for education categories will not reflect effects of education on BMI through income, and we may underestimate overall effects of education on BMI. But if our focus were on the effects of education on BMI through attitudinal and cognitive pathways, it is reasonable to remove effects of education on BMI through other pathways, so inclusion of income should be okay. Lastly, we should be aware that many causal relationships in the real world are reciprocal. For example, education may help to raise the awareness of health benefits of physical exercises, but some high school athletes may get college scholarships because of their good athletic records. Generally, it is very difficult to separate two reciprocal effects by analyzing cross-sectional data. However, in practice, if the dominant direction of causal influence between the two variables can be assumed, it is reasonable to set up a model based on the dominant direction. The results may still be biased, but probably not very much.